Hi, chemistry students. We started looking at electron configurations, and this can be kind of a tricky skill, so that's why I want to put this video together. So I'm going to start with something completely different. If anyone hasn't checked it out, the show The Queen's Gambit on Netflix, really cool. I really enjoyed it. It's a short miniseries. It's a little dark, it's a little depressing at times, but it looks at a female chess player, and it is wonderful, and that really inspired me to kind of pick up a chessboard and to learn a couple of things. And one other character that also inspired me, if anyone has seen the show Ted Lasso, Coach Beard is also a chess player. But I'll explain how the chess ties in. If you look at chess, it uses this really complicated notation. Q dash B4, Q dash N4, P dash QR4. It feels inaccessible, right? Maybe you've played chess at home. Maybe you've never actually played, right? Maybe you're like, okay, well, smart people play chess. I've played chess before. I'm not particularly good at it. But so recently, I actually picked up a book and I've been trying to learn it, right? I've been a little motivated to do something different. And what I found, rather enjoyable is learning how chess notation works, right? So the idea is your back row, you have the rook, the knight, the bishop, the queen, the king, the bishop, the knight, and the rook. The black square should always be in the lower left corner. Chessboards are typically shown from the view of the white player. White goes first. And the columns, right, you have rows 1 through 8. So the most common opening I've learned, and this is like, I've only learned this in the last week, so I beat a 12-year-old at chess, just to give you a little bit of background about what my chess has been like. I beat a 12-year-old, and I beat my wife, and I have lost to the computer on level 4 about 60 times. I have yet to beat the computer, all right? But again, I did beat the 12-year-old. The most common opening is king is pawn to K4, which means the pawn moves forward 2 spaces to the king's column, rank 4. All right. And if you watch the Queen's Gambit, they keep talking about the Sicilian defense. And I wanted to understand what that meant. I really enjoyed it. I enjoyed watching the show. What does that mean? There's all these different names, and I don't know any of that stuff. So I made it a point over the long weekend to learn a little bit about chess. And so the Sicilian defense is where black does pawn to QB4. That means queen's bishop, right? It's the bishop on the queen's side, that position in its fourth spot. So, what I've just been working on is just learning this notation. And then I feel like once you have that notation down, I'm reading different things that have strategies around it. But you have to learn that notation. It's like a gateway into this whole chess community. All right. Well, what we're doing in chemistry, these electron configurations, they're like that chess notation. All right. It kind of like, if you were to show this to anyone else, it's going to look like gibberish. All right. But to chemists, it's a notation of electrons, right? Chemists know electron configurations like quite well. And we get a lot of information from those configurations. Like, I can look at this. I don't even need to know it's sodium. I know it's sodium because of that 3s1 ending. I know how it's going to react. I know what it's going to do in different situations. There's a lot of information in here. And I, as a chemist, am able to decipher it. So that's why you guys are trying to learn this. It's a very, very big foundational skill. And I get that you might be sitting at home, you might be saying, Mr. Lupriato, I don't plan on being a chemist, and I never want to play a game of chess in my life. All right. Don't take that negative attitude. I think that this is a great opportunity, electron configuration, just to practice learning, because it's strange. I get that. And maybe, it builds this big foundation, but maybe we're not going to have these huge careers in chemistry. This is just one class we're taking to get by. All right. But I really believe that it doesn't need to be gibberish. It's accessible. And I really want everyone in this class to understand this information, right? Maybe we're not going to do a whole ton with it, but I want you to at least be able to understand the information and put it together in the questions that I ask you guys. All right. So the first thing I want to go through, 3 pieces of information. All right. They all need to come together. There is always a number, and then a letter, and then a superscript number. The first number just tells us the energy level. All right, we're gonna have energy levels 1 through 7. That's it. 1, 2, 3, 4, 5, 6, and 7. Nothing crazy there. The type of orbital, we've already seen in our previous video, we've seen in class, the 4 types of orbitals are S, P, D, and F. So you're gonna have some number 1 through 7 with the letter S, P, D, or F, and then there's gonna be a number. That superscript number is the number of electrons in that orbital. All right, S can hold up to 2, so it's either going to be S1 or S2. P can hold up to 6, so it could be P1, P2, P3, P4, P5, or P6. D goes all the way up to 10. F goes up to 14. So that's the system we're working with. Again, that first part is the energy level. There's up to 7 of them. That's how far the electron is from the nucleus. We can think of them as like rings in this point, but they're not rings, they're shapes. So you get the number and the letter. S is that sphere orbital, P that dumbbell, D the 4-leaf clover, and F that kind of tacky weird shape. All right, so we get 2 pieces of information. Now sometimes the orbitals, we think of them as like subshells or sublevels. First energy level only has 1 type of subshell. Second one has S and P. Third one has SPD. Fourth one has SPD and F. And then levels 5, 6, and 7 will go up to F. There are theoretical G and H and bigger orbitals, but we've never needed those, all right, because we've never had an element with so many electrons needing a space to go, all right? So, and again, that last piece of information, how many electrons fit, it is actually quite convenient for chemists to use boxes to represent the orbitals, right? S is always 1 box, and we could fit 2 electrons in there. P is 3 boxes, 2 in each box, 6 total electrons. D is 5 boxes, F is 7 boxes. All right, so we may have seen things like this in the past. We may have filled out charts where we did rings, but we want to think of them as orbitals now. So hydrogen, our simplest element, has 1 proton, which means it has 1 electron. Hydrogen's electron configuration is 1s1, right? First energy level, we always start at the smallest energy level. We start in the s orbital. It can hold up to 2 electrons. It only has to hold 1. Hydrogen, 1s1. Helium, all right, is going to be the second simplest, 1s2. So there's 2 electrons in that first energy level s orbital. 2 pieces of information, and then how many electrons. And remember, I've used this metaphor, the cars. There's 2 seats, right? Think of it as like a sports car, that s orbital. They're both filled up in helium. That's fine. All right. What about lithium? We're getting a little bit bigger. Lithium has 3 electrons. Its first 2 electrons are still in the first energy level, s orbital, so 1s2. Now we go to the second energy level, s orbital, and we only have 1 extra electron for lithium. So it'll be 1s2, 2s1. Beryllium has 4 electrons. All right, I hope you're seeing the pattern here. It's 1s2, because that's where we always start, 2s2. All right, that gives us 4 total electrons. We can add up these superscripts, and they'll tell us the number of electrons. All right, boron. This is not a boring one, guys. Boron has 5 electrons. 1s2 is its first 2 electrons, and we're always starting there. Then we go to 2s2. We still have 1 more electron. After 2s, we're going to go to p, right? Those are like our subshells, or different types of orbitals, 2p1. Don't say boron's boring. It's the first element with the p orbital. All right, carbon. Carbon has 6 electrons, 1s2, 2s2, 2p2. It adds up to 6. Now, P can hold up to 6 electrons. So let's keep going. We're going to do all the way through neon. Nitrogen, 7 electrons. First 2 are in 1s2. Then we go to 2s2. All right, what we've done at this point is we have configured the first 4 electrons. We know where they are, energy level and type of orbital. We have 3 more electrons, so we're going to go second energy level, p orbital. It can hold all 3 of them, 2p3. All right, the p orbital, 6 seats, right? It's like a minivan, right? It's a great one, you know, if you're, you know, it's like, you know, my dad said he'll drop us off as long as your dad could pick us up, right? Because we have enough space in the car. We have enough space for the electrons to go, space for people to go. Oxygen has 8 electrons. 1s2, 2s2, 2p4. All right. I really hope we're doing 2 more. We're going to do fluorine and neon. I hope that you are getting the point that we always start in the same place. We always start 1s. All right. Fluorine, 9 electrons. Let's go. 1s2, 2s2, 2p5. All right. And neon, 10 electrons, same pattern. First energy level, s orbital, 1s2. Second energy level, s orbital, 2s2. Second energy level, p orbital, 2p6. All right. So we use this trick called the diagonal rule. The way the diagonal rule works is we would write out 1s all the way down through 7s. Then we would do 2p down through 7p, 3d down, and 4f down, right? So each extra energy level introduces a new type of orbital until we get to the 4th one, and then we're like maxed out. And this is something that I would print out and I would give you, right? This would be the handout. If we had live school and we weren't as cautious as we are and as worried as we are, I would hand this to everyone right as you walked into the room. I would give you a sheet and this would be on it. This would be reference, all right, the diagonal rule. So the diagonal rule tells us the order of energy levels and subshells, all right? And it's kind of, I like to think of it as like the game Candyland. All right, if you've ever played Candyland, and I have a 5-year-old niece, so I've played a decent amount of Candyland over the summer. It's a pretty boring game. You start in the exact same spot and you just move in the same direction. All right, that's it. There's really no thought involved. All right. Now my niece, she kicks my butt in Candyland. She's like bragging like, "Oh, I'm so good at Candyland." You can't be good at Candyland. It is purely luck. You just flip cards over. It tells you exactly where to go. There's no thought involved. Right? I can't wait till she learns how to play chess so I can use all the knowledge I've been gaining now, and I'm just going to crush her. She's going to have no chance. All right? And that's going to be payback for all of those Candyland games that I've lost. Not bitter. All right? Anyway, all jokes aside, we just start in the same spot. We follow the diagonals. So if we're doing something bigger like sulfur, which has 16 protons, sulfur also has 16 electrons. This is electron configuration. We don't care about the protons or the neutrons anymore, right? That was last unit. That was nice. We put a little bow on it for the time being. This is all electrons. 16 electrons. Here's our order. The first 2 are in 1s2. All right, that leaves us with 14 electrons still to place, to figure out where they are. Second 2 electrons, 2s2, right? So we've done 1s2. We've done 2s2. This is how the diagonals work. Now we go 2p6. That gets us to 10. What comes after 2p? 3s, right? So we're going to go 3s2. All right, just quick counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have configured 12 electrons. There's 14. So there's 4 left. After 3s, we finish this diagonal. We start the next row. We are in 3p. Now we only need to place 4 more electrons. So it'll be 3p4, right? We don't have to fill it up, it's totally fine. This is sulfur's electron configuration, and this is how those diagonals helped us out. All right, still not that bad though, right? Sulfur, 16 electrons, not that bad. Let's go a little bit bigger. We're gonna do 2 more examples. Cobalt, 27. All right, starting in the same spot we always start, right? 1s2. Then we're going to go to 2s2, right? So we're just following those diagonals. Now we go to 2p6. All right, 3s2. And at any point, you know, we can stop and count. I'm pretty confident in this one. I know where it's going to end from years of chemistry experience. But at any point, you know, you can count those superscripts. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12. We have 27, so we need 15 more electrons to figure out where they are. All right, so 3p6, right? That brings us down from 15 unconfigured electrons to 9. Now watch this. What might you expect after 3p? You would logically think 3d, but look at the diagonal. It's 4s. And this is something really important that I want you to take note of. S always comes after p. Just the way it works, the fourth energy level S orbital shows up before the third energy level D orbital, which is why we can't just write 1s, 2s. This is why we have to actually use this diagonal rule, right? So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d. All right, this is like the first spot that people are going to get caught, right? If you're playing Candyland, that's like your first like go back to start type thing, right? Everything's been easy up until 3p6, but then we get 4s. All right, let's double check. We need 27 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 gets us to 4s2. Since it's 27 and D can hold up to 10, it will be 3d7. All right, that is Cobalt's configuration. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d7. It seems weird. In like a week, you're gonna have these down, and you know you're just gonna know these. All right, and then you're gonna be cool. You and your friends, you're gonna try to form a band. You're gonna be like, let's use the electron configuration for silver, and you know maybe 4d10 will be the name of your band, and no one knows why that's the name of your band, and you're like, well, it's chemistry, so that's what's up. All right, or maybe that's just me. Who knows? Last example in this video. This is a big one. This is a tough one. Lead. Lead has 82 protons. That means 82 electrons need to get configured. That's a lot of electrons. It's a lot of math. We can handle it. We have the path. We just got to take it slow. 1s2. We start where we always start. 2s2. All right. 2p6. We're going to be going for a little while here. This is a big guy. 3s2, 3p6, right, following it along, 4s2, 3d10. This is probably going to take 2 lines, actually. It's going to be so big. All right, what comes after 3d10? 4p6. And what always comes after p? S. So we're going to go 5s2. All right, after 5s2, we're going to go to 4d10. Why don't we take a second here and count up how many electrons? This is actually going to be 2 rows, this answer. So let's count up our electrons. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, plus 2 is 20, plus 10 is 30, plus 6 is 36, plus 2 is 38, plus 10 is 48. So we've configured 48 electrons in this top row, all right, which means we still have 34 more electrons, all right? And again, if you need to use a calculator for this, by all means do that, all right? Because I don't want to see anyone getting these questions wrong because you made a silly counting mistake, all right? Anyway, we have just completed 4d10. Where are we going next? 5p6. And right, we have 48 as a reference. So if we add 6, it gets us to 54 electrons. All right. Now we're going to add 6s2. All right. So we went from 48 to 54 to 56 electrons. What comes next? 4f14. So remember how 3d was, it's like 1 less than 4s, right? So those d energy levels are always 1 less than everything they're near, right? So it's 4s, 3d. If it's 5s, it's 4d. It's always 1 less, the d orbital. Well, the f orbital is 2 energy levels less. So 6s, 4f, right? So we're going to get 4f14. And then after 4f14, we go 5d10. All right, let's double check our math again. We had 48 electrons. We added 6 more. That got us to 54 electrons. We add 2 more. That gets us to 56. We add 14 more. That gets us to 70. We add 10 more. That gets us to 80. So we're at 5d10 and we have 80 electrons. We're trying to configure 82. So this is going to end 6p2. All right, and that gets us 82 electrons. You can always add up all of, and I'll put them in a different color for a second here. You could add up all of these subscripts, right? All of those subscripts, or superscripts, excuse me, all of those superscripts should add up to 82. All right, and we followed the order using that diagonal rule as reference, and we came up with the electron configuration. So obviously, practice is going to make perfect. I have done a lot of electron configurations. I have a lot of practice under my belt. I'm pretty good at it. You guys are new to it, but we're going to stay with the smaller elements. We're going to practice it, and we're going to get really good at it. All right, so I want us to be successful with this skill of electron configuration, and I think we'll get there. All right, so that is electron configuration.